Alrighty, so I did the math and it looks like if I can record 4 40-minute lessons, I should be able to cover our 3-hour lecture class from today. So I do have 2 lessons already posted for you. Let me go ahead and just double check. This is my third video. Let me try to reopen the Canvas app. So I'm trying to put all these lessons, not all, I'm just gonna have 4. So the first 2 are now posted. The first one is 37 minutes, 30 seconds. The second one is 36 minutes. This is gonna be another like about 40-minute one. And then I think I should be able to finish section 2.5 possibly in another video. But now let us go over the 3rd and 4th page of section 2.4, okay? I know you have that already downloaded or printed. On my second video, we went over 4 examples of exponential growth functions. They don't really do much derivatives. We did derivative on example 1C, and the other ones were just really solving equations involving natural logs. So I do miss doing some more calculus, and I think page 3, now something new. So this is just slightly different way of thinking, but we've been working with this the whole time. So let me go ahead and give you an example. If you have f of x equals, I'm gonna make up something. I mean, I don't have to make up anything. I got good examples down here. So we're gonna find f prime of x here. Okay, so if f of x is 2 times e to the 3x, because we're reviewing, let me do this the longer way, and then we're gonna come up with a pattern, okay? F prime of x is 2 times e to the 3x power times the derivative of 3x, right? So f prime of x is 2 times e to the 3x power times, now what's this going to give us? That's just going to be 3, right? I want you to notice a pattern. So every time we're going to copy down that e term, and then multiply that by the derivative of this power, okay? So what about the second one? And I'm not going to simplify it to 6, okay? I'm just going to leave it like that. If I take the derivative of this, what will happen is I will just multiply this original function by derivative of 3x, right? It's kind of boring because I got 3x. I may change it to something else, but that will just be 5 e to the 3x times 3, right? That's what f prime of x is. I'm going to change this because this 3 is boring. I want you to see the pattern. How about I change that instead of 3x as a denominator, with the power, how about I change it to negative 4x? Well, what will happen? Well, I have to take the derivative. So copy down that function exactly the same. But then I must multiply this by the derivative of negative 4x. Okay? So this won't change. But I will multiply that original function by that f of x by what number? Negative 4. Are you seeing the pattern here? So f prime of x for the last one is 0.25 e to the 3x power times what? 3. So functions of the form f of x equals a constant c, any constant c, times e raised to the kx power have the property that the derivative is always going to be that function times that constant multiple k of the function. So that's why we were multiplying the function f of x times 3 and 3, and this one was getting multiplied by negative 4, and this one was getting multiplied by 3. So that's one of the theorem. Well, here's a theorem for you. So if you have a function in the form f of x equals c to the times e to the kx power, then the derivative of that function is, I'll go ahead and write the k first, k times c times e to the kx power. So the derivative is really k times the original function f of x, okay? So if I'm using the dy dx notation, what we can say is derivative of y with respect to x is just going to be some constant k times its original function, okay? So that's what's happening. We noticed that on the first 4 examples. So they may ask you a question like this here. Find a function that satisfies each equation. So what we are saying is a function a, derivative of a with respect to x is 5 times the function itself a. So I'm going to go ahead and write down the function using this rule, theorem 9, okay? So a of x, the function must be, okay, some constant c times e raised to the 5x power. Now this is what I think the answer is. I will circle it. But in order to find, in order to check our answer, let's actually find the derivative. So here's the check. What's a prime of x? We're going to keep that c, okay, times e to the 5x power, and we'll multiply that by 5, right? And that's true. Now, we're looking at a derivative who is equal to 5 times the original f of x, I'm sorry, a of x. So in a different writing, we are saying this is dA dx is equal to 5 times a. So this is true. And you can skip this checking part as long as you understand this is a special type of function whose derivative is equal to constant times its original function. Now let's try this one. So they are saying, hey, the derivative of f of x is 7 times the original function. So f of x must be in a form where we have a constant times e to the what x? 7x. So we can go ahead and take the derivative. I mean, this is the answer, but let's try to take the derivative of this function so that we to agree if that's true. So if I take the derivative of c e to the 7x, I'm going to have to write that down first, and then I will have to multiply this by what number? 7, right? Because that is the derivative of 7x. Okay? So we got that f prime of x is equal to, now what is this? That's the original function, right? That's f of x times 7, and that is what they wanted. That is what they wanted. So what we are given is, and this was just a check, what we are given is the property, the theorem that states that if we have a function in this format, y equals constant times e to the kx power, its derivative is going to be that constant k times the original function. So we're given, it's almost like a backward, right? So what I'm doing is I'm writing a function and I'm actually taking the derivative of that function to see if the statement is true. All right. I got a text message. All right, now let's take a look at this one. This is saying dn dt, derivative of this function. So the function is like n of t. Okay, the derivative of n of t is equal to 0.05 times n of t. That's what they are saying. So what kind of function is like that? So let's see. N of t must be c times e to the kt, right? Kt power, but k is 0.05. And I mean, I think you guys should write something down. Like you're like, oh, all right, I'm going to try to write this down. And then you can check by actually finding dn prime of t. That will be, I copy down the exact same function. And then I multiply this by 0.05. Why? Because 0.05 is the derivative of 0.05t. So that is saying dn dt is equal to, now what is this? This is n, isn't it? This is n of t, n times 0.05, and this is what they wanted, okay? So because we practiced finding the derivative of an exponential function with base e, and we got really good at it, hopefully, we can go ahead and do this backward thinking, okay? The very last one, let's try this one. they're saying dp dt is equal to some constant m times its original function. So let us find this function p of t. Okay, let's find this function. It's going to be c e to the, now what is the constant? The constant is the number that's getting multiplied by the original function, right? So the previous one, it was 0.05, it was 5, it was 7. Now here they didn't give me a number, but they gave me m, so I'm going to say m, and then we need r, t. So, okay, and this one is very abstract. I mean, there's no number or anything, but if I want to go ahead and check this, I can find the derivative of this. So what is p prime of t? Okay, we're taking the derivative of this c times e to the mth power with respect to t. Okay, I need to find the derivative of m times t. Okay, and that is going to be, simply going to be m. So what we are looking at is that p prime of t is equal to p times m, and that is what they wanted up there, right? So that was a quick check. We checked it. But this checking part isn't really necessary. If you can, I mean, I'm sure you can just quickly check in your head. But this is a cool property, and this will make our life much easier so that we don't have to write the derivative function. We can go ahead and use this property to solve the application problems that we kind of talked about on the second video. So let's see. I got example 6 and 7. This will be a shorter video. In business, interest compounded continuously. So what we know is that A equals P times E raised to the RT power. Now, if you take the derivative of this, you will have the P times e to the RT, right? But then you're going to have to multiply this by derivative of RT. Okay, what happened is that we're going to get A prime is equal to P times E raised to the RT power times R. Okay? And you're like, what is going on? But you know what? The beautiful thing is you guys use this already. You did this when we were doing that investment function or like a whole bunch of application problems that we did. I want to show you, I want to convince you that you actually did it. Like this one right here. When we were finding the derivative, I don't know if you remember, we were multiplying that leading coefficient, that 55,000 by the constant on the power. So we multiplied it, and that's how we got that number. So we've been doing this the whole time. We're just trying to come up with a general rule with some variables this time. So I can do R times P, and that's going to get multiplied by E to the RT powers. But you see, this is the same thing as we were talking about up here on example 5. So without all that, when they made it easy for us, they gave us the equation. They gave us the equation right there. Okay? Let me keep reading though. Suppose P naught in dollars is invested in the Von Neumann High Yield Fund with interest compounded continuously at 7.2% per year. Now 7.2%, that is your R. R is equal to 0.072. So if I plug in that R into this function, what we get is the derivative of this function is R of 0.072 times the original, the compounding continuous function. So we could have come up with that rule, but they gave us to us. Just in dp dt notation, so instead of calling it A, they called it P. Their function name is P. But now, guys, I did all that extra kind of work on top with this blue pen, but I can go ahead and erase it if that was confusing. Okay, don't worry about it. But I'm sure you can follow that. But let's just go ahead and use what they gave us, because this is a nice problem. They gave us what to use. They said at this point, that is at any point in time after T years, the balance P in dollars per year is growing at the rate dp over dt equals 0.072 p. Now, from looking at this, we should be able to come up with the equation. P is equal to C times. Now here, let me go ahead and replace the C with P naught. Okay, that's the initial value. Okay, P naught times E raised to the 0.072 T. So if I ever want to know the actual amount of investment, this is what I'm going to use. But if I want to know the rate of change, I will use the given equation. This is going to give us the rate of change. how fast our money is growing. All right, I'm gonna have to pause this real quick, hoping that I could put this together because I feel like I'm getting a very important call. So I was going for about 15 minutes. I got a phone call, so I have to stop recording. I'm gonna try to figure out a way to combine these two videos so that I don't have like two different videos. But I'm gonna continue example 6. So if I want to find the rate of change, I will use this purple boxed equation. If they ask me to find the actual value of the investment, this is what's going to help us find that. So let's see. Find the function that satisfies the equation. We did it already, guys. Write it in terms of P naught and 0.072. So we wrote it already. So the equation P of t, the input is going to be time, is equal to some P naught, that initial investment, getting multiplied by e raised to the rate of 0.072 times however many years t. So this is the equation that will satisfy this is the function that will satisfy this equation. And this is similar, the same as the 4 examples that we just kind of did, using P naught instead of C. Okay, so that's the only difference really. All right, now what? Suppose $10,000 is invested. What is the balance after 1 year? Okay, if they just want the balance, I can go ahead and plug in 1 into my function. But P naught is how much? 10,000. So they're investing this initial $10,000. I'm gonna go ahead and plug it into that function that I found. E raised to the 0.072 times 1. So not t anymore. After 1 year, it's just gonna be 1. So let's go ahead and plug this into our calculator. 10,000 times e raised to the 0.072, which is $10,746.55. Okay, no crazy rounding rules like rounding to the nearest million or anything, but this person earned $746.55 after 1 year in interest. That's good. All right, what about in 5 years? Money should be bigger, right? 10,000 times e raised to the 0.072 times 5. All right, if I type that in, we get the amount of money to be, oh, let me go ahead and draw the dollar sign. We do want to know what the unit is. This one is, wow, it grew a lot. $14,333.29. So here we were using that newfound function that we wrote on part A, and we were able to answer the 2 questions. And they're asking, what is the rate of change of the balance after 1 year or after 5 years? Now listen, we're going to now use, because we see how they're asking for the rate of change. The rate of change. And I was talking about if they want the rate of change, we're going to use this given equation. So what they are saying is this. The derivative is equal to that rate times the value, the p-value. Okay? So let me show you, okay? So what we are finding is, p prime of 1. Okay? I mean, we're supposed to find the derivative and plug it in 1 and everything, but we don't need to do that. What we know is that derivative at 1 is going to be equal to that number, that constant times p of 1. We know what p of 1 is. We found it a line above. So we're going to multiply 0.072 times $10,746.55. Let's go ahead and find out what that is. Get my calculator. 0.072 times $10,746.55. That comes out to be $773.75 rounded per year. So after 1 year, that is the rate of change of this investment. Let's go ahead and find the other one. What is p prime of 5? I don't need to find the derivative. They already gave us the rule. The derivative, the p prime of 5 is equal to 0.072 times the function value at 5, p of 5. And we found that number above, so we're going to go ahead and multiply that constant by $14,333.29. I love how we get to use this rule given instead of finding the derivative. So 0.072 times $14,333.29. So it must be growing at a faster rate because the money is bigger. What they are compounding based on is bigger. So $1,031.99. How awkward. Let's go ahead and round that up to $32 then. And the unit is per year. Okay? So that's how you can use this fun way of writing the derivative as a product of a constant, the rate times the original function. And another one similar, and this one will be my last example for this video. This is going to be a shorter one, but that's okay. Life science, population growth in China. I know they are growing. In 2017, the population of China was 1.39 billion. Oh, and the exponential growth rate was 0.44% per year. Okay, thus, here's the average rate of change function for Chinese population. So I see that the rate is, they converted the rate into a decimal. So this is the rate. Rate is 0.44%. And they just converted it into 0.0044. So what they are saying is, hey, the average change at any given year is going to be that constant, that rate times the function value at that year. So how many people that they have in that particular year times this rate. Alrighty, let's go ahead and write the equation first then. They said write the function that satisfies the equation. So I'm gonna say population of China, P of T, is equal to, now I was gonna go ahead and write a C, but then they gave us the initial population in not year 0 or anything like that, but only in year 2017. So P naught times e raised to the r times t power. Okay, I'm going to go ahead and plug in everything I know. P of t is equal to 1.39 billion times e raised to the r is, now I'm sorry, I keep using r, but I think this example love to use k. So k times t, I'm going to change that to k times t, where k is 0.0044 and t is just that unknown input value, however many years is it from 2017. So we wrote the function. Now let us use this function to estimate the population of China at the beginning of 2020. To find the t first, subtract 2022 by 2017. It's pouring outside in Fredericksburg. I am enjoying this weather. I contacted my babysitter to see if she can come back tomorrow or even next week. I might have to find another care. Oh my goodness. All right, so t is 5, you guys. So we're going to plug in 5 into this function. What is p of 5? 1.39 times e raised to the 0.0044 times 5. So 5 years later, how many Chinese are we going to have in this world? 1.39 times e raised to the 0.0044 times 5. I got 1.42 billion Chinese. Okay. So estimate the population of China. It's going to be 1.42 billion if they follow this growth pattern, if this continues. Now find the rate of change of China's population. Okay, now they want you to find the rate of change. Now for the rate of change, we're going to use that dPdt, derivative of p with respect to t is equal to that rate times how many people we have in that year. Okay, so we're going to go ahead and use what they gave us. So what we are finding is p prime of 2020, right? So remember 2020 is t equals 5. So p prime of 5 is equal to that constant 0.0044 times how many people they had in 2022. And that's going to be 0.0044 times 1.42 billion. Okay, so let me get my calculator. 0.0044 times 1.42 got me 0.0044 0.006248 billion. But it's too small. So I'm going to go ahead and multiply this by 1 billion to just get a number of people. So I'm going to multiply this by 1 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. So what I'm getting is 62. All right, let me write it down and read it later. This is a big number. Let me go ahead and write the number down and put some commas. So this is what I got. Okay, so 6,248,000 people per year. Their population is increasing that fast. So I just wanted to kind of convert. I'm just going to minimize that a little bit. Okay, so that's good. Or move it so that it's not, okay, that's looking good. So wow, the Chinese population is growing, and it's growing at 6,248,000 people per year in 2022. So that will be my final answer, and that is the last answer of 2.4. Now I may be able to just continue. No, I won't do that. I will stop it so that you guys can get a break. Now, we are done with exponential growth function application problems. When I come back, I'm going to go ahead and continue with 2.5, which is almost the same thing, but with exponential decay functions. So you'll see a lot of these. But I will go ahead and post a note for 2.4 right now. Oh, guys, I love this. So I'm going to go ahead and leave them a 5-star review. But let me stop this video so that I can process it and put